take a deep breath, like just pull the air right into your lungs. The oxygen you just breathed in, it actually didn't exist at the dawn of the universe.
No, it didn't. The Big Bang only really gave us the absolute simplest ingredients.
Right, like hydrogen, a little helium, and, a tiny trace of lithium. So that oxygen keeping you alive right now had to be manufactured somewhere. It
Exactly.
was literally forged in the fiery, crushing core of a dying star billions of years before the Earth even formed.
It really is one of the most profound realizations in modern astrophysics. The universe had to build its own building blocks, one atomic element at a time, through this incredible mechanism of extreme heat, pressure, and gravity.
Yeah, and understanding that mechanism is exactly why we are here today. So welcome to part 1 of our 20-part deep dive set.
Glad to be here.
If you are an honors student prepping for the New York Regents Exam, our mission is to help you absolutely crush this test.
We really want you to ace it.
We do. We are taking the very complex astrophysical concepts on your study list and, well, unpacking the actual physics behind them.
Right, we aren't just memorizing definitions here. We are looking at how the universe actually operates.
Exactly. And today's focus is stellar nucleosynthesis.
Which is a term that often intimidates students.
Oh, for sure. It's a mouthful.
It is.
Yeah.
But breaking the word into its roots tells you the whole story.
Yeah.
So stellar means star.
Right.
Nucleo refers to the atomic nucleus.
Okay.
And synthesis means to create or combine.
So we are quite literally talking about how stars act as giant cosmic factories to synthesize new atomic nuclei.
Exactly. They're factories.
Okay, let's unpack this. Because the engine of this cosmic factory relies on a very specific process, right? Called fusion.
Yes, fusion is the key.
But to understand fusion, you first have to understand why atoms don't want to fuse in the first place.
Right, they really don't want to.
Because atomic nuclei are positively charged, and basic physics tells us that positive charges fiercely repel each other.
Yeah, that is the electromagnetic force at work. If you take two positively charged protons and try to push them together, they act like two repelling magnets.
Like when you try to push the north poles of two magnets together and they just slip away?
Precisely. The closer they get, the harder they push away from each other. That invisible barrier is incredibly strong.
So how does the star force them together? It seems like you'd need an insane amount of speed and pressure to overpower that repulsion.
You do. You need a core temperature of about 15 million degrees Celsius combined with just crushing density.
Wow. 15 million degrees.
Yeah. And at those extremes, the hydrogen nuclei are moving so fast that they slam into each other before the electromagnetic repulsion can even push them apart.
They just crash right through the barrier.
Exactly. And when they get close enough, an even stronger force, which is the strong nuclear force, takes over and just snaps them together.
And that is fusion. Two lighter elements are forced to combine into one heavier element.
You've got it.
So to visualize the energy release here, I like to imagine holding two incredibly powerful repelling magnets. Like you force them together with all your strength, and the second they finally snap together, a tiny sliver of the actual metal completely vanishes.
Right.
And it transforms instantly into this blinding flash of pure heat and light.
What's fascinating here is the sheer efficiency of that transformation.
Yeah.
Yeah, is the direct physical manifestation of Albert Einstein's famous equation EMC was.
Oh, right. Energy equals mass times the speed of light squared.
Exactly. When those lighter elements fuse, the new heavier element they create actually has slightly less mass than the original pieces did.
Wait, really? It weighs less?
It does. That missing mass is converted directly into energy.
Oh, wow. And that energy release is what keeps the star alive.
Yes, it creates an outward explosion that constantly pushes back against the immense weight of the star's own gravity.
Which introduces a vital concept, hydrostatic equilibrium, right?
Yes, hydrostatic equilibrium. The star's entire life is basically a delicate tug of war.
Gravity versus fusion.
Exactly. Gravity is constantly trying to crush the star inward, while the energy from fusion is constantly pushing outward.
So as long as the star has fuel to fuse, the forces balance and the star shines steadily.
Right. But the exact menu of elements a star can synthesize during its lifetime is strictly dictated by its total mass.
Mass is destiny when it comes to stars.
It really is.
So let's look at the first major category you need to know for the Regents exam. Low mass stars.
Good place to start.
And the cutoff point to remember here is 8 solar masses. A solar mass is simply the mass of our sun, right?
Right. One solar mass equals one sun.
So any star with less than 8 times the mass of our sun, falls into this low mass category.
And our own sun is a classic example of a low-mass star.
Now, I would think that having less mass means the star has less fuel, so it must burn out much faster, right? Like a small campfire burning through its wood way faster than a massive bonfire.
You would think so, but actually it operates in the exact opposite way.
Oh, really?
Yeah. In astrophysics, the more massive a star is, the harder its gravity crushes down on the core.
Okay, that makes sense. More weight, more crush.
Right. And that intense crushing forces the massive star to burn through its fuel at a furious, frantic rate just to hold itself up.
Oh, so the little guys have it easier.
Exactly. A low-mass star has much less gravity squeezing its core, so it burns its hydrogen fuel slowly and steadily over billions of years.
So they are the slow burners of the universe.
They are.
And right now, our sun is in that slow burn phase, fusing hydrogen into helium. But eventually, that hydrogen fuel is going to run out.
It is.
The core will just fill up with helium. What happens to the factory then?
Well, when the core runs out of hydrogen, that outward push of fusion energy suddenly stops.
Uh-oh.
Yeah, the tug of war is lost. Gravity instantly takes over and begins crushing the helium core.
Because there's no explosion pushing back anymore.
Right, and as the core is squeezed, its temperature spikes dramatically. It gets so hot that the star can now overcome the repulsion of the helium nuclei.
So it upgrades.
Exactly. It begins fusing helium into even heavier elements, primarily carbon and oxygen.
But low-mass stars hit a ceiling, right? I mean, their gravity simply isn't strong enough to squeeze the core hard enough to fuse anything heavier than carbon or oxygen.
That's correct. A low-mass star's factory just maxes out.
It just doesn't have the muscle.
No. Once the helium is used up, the core is mostly carbon and oxygen. Gravity tries to crush the core again to trigger the next stage of fusion, but a low-mass star simply doesn't have the gravitational weight to generate the temperatures required to fuse carbon.
So the nuclear engine permanently stalls.
It does.
So what does this all mean for the end of the star's life? Because, we are so conditioned to think that all stars die in these massive apocalyptic explosions.
Right, like in the movies.
Yeah. But a low-mass star actually has a rather quiet exit, doesn't it?
It does. Without the intense heat of fusion to hold it together, the star's outer layers of leftover hydrogen and helium just, well, lose their grip.
They just drift away.
They simply drift away into deep space, expanding outward in this beautiful, glowing shell of ionized gas.
Which astronomers call a planetary nebula.
Yes, a planetary nebula.
It's like a cosmic dandelion. The wind just gently blows the fluffy outer seeds away into space.
That's a great way to picture it.
But what happens to the core? That superheated ball of carbon and oxygen is just left sitting there in the middle of this expanding cloud.
Yeah, the naked core is left behind, completely exposed. And we call that remnant a white dwarf.
A white dwarf. Got it.
It is no longer doing any fusion. It is essentially a fossilized star core.
Wow.
And it is incredibly dense. I mean, a single teaspoon of white dwarf material would weigh several tons on Earth.
That's insane, a teaspoon.
Yeah, and over billions of years, it will slowly radiate its residual heat away into the coldest space until it eventually turns dark.
But the planetary nebula, that dandelion fluff floating away, that's highly significant, isn't it?
Extremely significant.
Because the star just spent billions of years creating carbon and oxygen, and now it's releasing those newly minted elements back into the galaxy.
Right.
It is seeding the universe with the basic building blocks of life.
It is a vital cosmic recycling program. However,
There's a catch.
there is. If low-mass stars can only manufacture elements up to oxygen or occasionally neon, we have a major puzzle to solve.
Because the periodic table is full of much heavier elements.
Exactly. Silicon, calcium, iron. To forge those, you really have to turn up the heat.
Okay, here's where it gets really interesting. To get those heavier elements, we have to look at the second category on your review sheet. High-mass stars.
The heavyweights.
Right. These are the stars with more than 8 solar masses. And because of their immense bulk, they operate like giant cosmic pressure cookers.
A pressure cooker is an excellent mechanical analogy for this.
Yeah.
A high-mass star has significantly more mass, which means it exerts an unimaginably strong gravitational pull on its own core.
So if you think about a pressure cooker on a stove, it has a heavy locking lid that traps the steam inside.
Right.
And as the heat rises, the pressure becomes incredibly intense because the steam has nowhere to go. In a high-mass star, gravity acts as that heavy, inescapable lid.
That's a perfect way to visualize it. It squeezes the core so violently that it cranks the internal temperatures to billions of degrees.
Billions.
Yes, and those extreme temperatures allow the high-mass star to force heavier and heavier nuclei to fuse.
Because of that electromagnetic repulsion we discussed earlier.
Exactly. A carbon nucleus has 6 protons. Oxygen has 8.
So the more protons you have, the stronger the repulsion.
Right. It takes staggering speed and heat to smash 2 carbon nuclei together.
But the high-mass star has the gravitational muscle to actually do it.
It does. So while the low-mass star stalls out and dies, the high-mass star just shifts into a higher gear.
It just keeps going.
It fuses carbon into neon. Then it fuses neon into oxygen, oxygen into silicon, building heavier elements in distinct layers. Almost like, well, like the layers of an onion.
An onion.
I like that. The core structure literally resembles an onion. The outermost layer is fusing hydrogen. The next layer down is fusing helium, followed by carbon, neon, oxygen, and silicon, all the way down to the super-dense center.
But eventually, even these giant cosmic factories hit a hard physical wall.
They do.
The core starts building up iron, and specifically a closely related element, nickel. And that is where the fusion train completely derails.
Completely.
Why is iron the ultimate dead end for a star?
What comes down to a concept called nuclear binding energy. Up until iron and nickel, every time the star fused lighter elements into heavier ones, the process released energy.
It paid a dividend.
Right. And that energy pushed outward and kept the star from collapsing. But iron and nickel have the most tightly bound nuclei of all atomic elements.
So they are incredibly stable.
Extremely stable. Because they are so tightly bound, fusing iron into anything heavier doesn't release energy.
Wait, it does this?
No, it actually consumes energy.
Oh, wow.
Trying to fuse iron acts like a fire extinguisher being sprayed directly into the core of the star. It actively drains the energy that is holding the star up.
So the engine doesn't just stall, it goes into rapid reverse. The outward pressure disappears entirely.
Instantly.
And without that outward pressure, gravity wins the tug-of-war instantly. The entire colossal weight of a star, more than 8 times the mass of our sun, comes crashing down on the core all at once.
And that collapse happens in a fraction of a second.
A fraction of a second. That's terrifying.
It is. The core is crushed down until the atomic structure itself actually breaks.
Wow.
The outer layers of the star rush inward at a massive fraction of the speed of light. They smash into the hyperdense, unyielding core and then rebound violently outward.
And that rebound, that catastrophic shockwave, is a supernova explosion.
Yes. The star literally tears itself to pieces.
But hang on, this brings up a huge contradiction.
Okay.
If standard fusion fundamentally stops at iron because it drains energy, how does the universe create all the elements heavier than iron?
That is the big question.
Right. Because the periodic table has iodine, silver, gold, platinum, uranium. Where do they come from if the star can't make them?
To build elements heavier than iron, we have to look past standard fusion. We rely on a completely different mechanism that your study guide highlights, called neutron capture.
Neutron capture. Okay, let's visualize this process because it is wild.
It really is.
Imagine the atomic nucleus, let's say an iron atom, is a player standing on a cosmic dodgeball court.
Okay.
In an extreme astrophysical environment, there are countless free neutrons flying around at terrifying speeds.
Right.
The iron nucleus acts as a catcher. As neutrons fly by, the nucleus absorbs them. Once the nucleus catches enough extra neutrons, it becomes unstable, undergoes radioactive decay, and transforms into a brand new, heavier element on the periodic table.
The mechanics of your dodgeball analogy highlight a real crucial detail.
What's that?
Why neutrons? I mean, why not just throw more protons at the nucleus?
Because protons are positively charged. If you throw a proton at an iron nucleus, the electromagnetic force will just bat it away.
Yeah. Exactly correct. But a neutron has 0 electrical charge.
Ah, so it doesn't care about the magnets.
Right. It acts like a ghost, completely bypassing the electromagnetic barrier. You can just drift right into the nucleus where the strong nuclear force grabs it and locks it in.
But this raises an important question. If an iron atom is just sitting there waiting to catch neutrons, where is the massive supply of high-speed neutrons actually coming from?
Well, your review sheet points to a very specific chaotic version of this called rapid neutron capture, or the R process.
The R process.
The rapid part is key. The atom is bombarded with neutrons so fast that it doesn't even have time to decay before it catches another one.
Oh, so it just bulks up incredibly fast.
Yes, allowing it to build up to incredibly heavy masses like gold and uranium. And the only environment chaotic enough to provide that kind of intense neutron bombardment is the supernova explosion itself.
Wait. I need to pause here.
Sure.
So the gold in a wedding ring or the trace amounts of platinum used in the circuitry of the computer you're studying with right now,
Yeah.
none of that was manufactured during the millions of years the star was happily burning and shining.
Not a single atom of it.
That is wild. The heavy metals were entirely forged during the final chaotic milliseconds when the star was actively exploding.
Yes. The supernova shockwave itself slams the neutrons into the atomic nuclei to build those heavy elements.
That is astonishing.
It perfectly illustrates the sheer scale of energy required. Building the heaviest elements in the universe requires an environment of such extreme violence and heat that it can only occur during the explosive death of a massive star.
Okay, so the high-mass star explodes. The supernova shockwave forges the gold, the platinum, the uranium in a fraction of a second.
Right.
But what happens to the factory? The star is gone. What happens to all the heavy elements it just made?
This brings us to the final main concept on your review sheet, which is supernova scattering.
Supernova scattering.
When the high-gas star detonates, it forcefully ejects everything it ever created deep into interstellar space.
So it doesn't just keep it.
No, the carbon, oxygen, and silicon from its onion layers, plus the heavy gold and uranium forged in the explosion itself, are blasted across the galaxy.
It's the high-mass equivalent of the low-mass star's planetary nebula. But instead of a gentle dandelion puff, it's like a shotgun blast of cosmic shrapnel.
Exactly. And that shrapnel drifts through space, eventually colliding and mixing with vast, cold clouds of hydrogen gas.
And then?
Well, over millions of years, gravity begins to pull those newly enriched clouds together. The gas collapses, heats up, and ignites to form a brand new generation of stars.
And the leftover dust and heavy elements swirling around those new stars begin to clump together.
Right.
They form asteroids, moons, and rocky planets.
If we connect this to the bigger picture, this entire cycle of stellar nucleosynthesis is the fundamental mechanism that shaped the physical world you inhabit.
It's literally how we got here.
Exactly. Astrophysicists don't study stellar life cycles just to categorize glowing dots in the sky. They study them to track the chemical history of the galaxy.
We are literally studying our own origin story.
We really are.
Think about this as you sit at your desk right now. The rocky crust of the Earth, the calcium forming your skeleton, the iron in your blood that binds to the oxygen you just breathed in.
Yeah.
Every single atom in your body, heavier than helium, was assembled inside the core of a star or forged in the explosive shockwave of a supernova. We are constructed from the recycled debris of dead stars.
It is a profound, scientifically verifiable truth. We are intimately linked to the cosmos because we are quite literally made of it.
I love that so much. Okay, take a moment to stretch, shake off the existential awe, and let's lock in this knowledge so you can walk into your exam with total confidence.
Do it.
You've tackled part 1 of this deep dive series, and you are already ahead of the curve because you now understand the mechanics, not just the vocabulary.
Let's do a rapid-fire review of the crucial terminology and cutoff points you need to master for the Regents exam.
Perfect. Term 1, nucleosynthesis. This is the overarching process of stars acting as factories to manufacture new elements.
Term 2, fusion, the mechanism of that factory. Crushing lighter atomic nuclei together at extreme speeds to overpower electromagnetic repulsion, creating heavier elements and releasing energy through EPA4.
Term 3, the mass cutoff. The magic number to memorize here is 8 solar masses. Less than 8 is a low-mass star. More than 8 is a high-mass star. Mass is destiny.
Right. Term 4, low-mass star life cycles. They are the slow burners. They eventually fuse helium into carbon and oxygen, but lack the gravity to go further.
And they end their lives by gently puffing off a planetary nebula and leaving behind a dense, glowing white dwarf.
Exactly. Term 5, high-mass star life cycles. They are the pressure cookers.
Right. They fuse heavier elements in onion-like layers until they hit the ultimate dead end, which is iron. Iron consumes energy, stopping the outward pressure and causing the core to instantly collapse.
In term 6, neutron capture and the R process. This is how the universe builds elements heavier than iron. Because neutrons have no charge, they can bypass the electromagnetic barrier.
And during a supernova, the rapid bombardment of neutrons forges the heaviest elements on the periodic table.
Finally, supernova scattering. The violent explosion of a high-mass star blasts its newly forged elements out into space to eventually form new nebulas, new stars, rocky planets, and eventually us.
You have the mechanics down perfectly.
You are well equipped to handle any question they throw at you regarding stellar life cycles.
But before we let you go get back to studying, I want to leave you with one final mind-bending thought to chew on.
Ooh, what is it?
We talked about how the heavy elements were blasted out into space by ancient supernovas, right? And those elements mixed around in a giant cosmic cloud before forming the Earth and eventually you.
Right, the mixing process of a solar nebula is vast and chaotic.
Exactly. Which means the atoms that make up the physical structure of your left hand and the atoms that make up your right hand.
Oh, wow.
They almost certainly originated in the explosive deaths of two completely different stars, separated by countless light years and billions of years of time.
That is amazing to think about.
You are a mosaic of different cosmic explosions.
You really are.
Keep that stellar perspective in mind as you prep. You've got this, and we'll see you for part 2.